I tried again to send you the email. I don't know why you're not receiving it. Any of you have received the email? You have received? You too? So, you don't?
No.
Okay, I'll try it again. Otherwise, if you can present to the, because I added in the list. You will have, if you have received the email, you will have in CC all the group. So,
Okay.
No. It's strange because you have CRBNet account. Also, Benedetta, you have CRBNet account. You can receive. You have CRBNet.
I'm looking at
Okay.
that right now.
Okay. Anyway, this morning we have covered. Well, yesterday and this morning we have covered how to solve the problem if it is a steady state problem, if it doesn't vary with time. We did all the equations, discretization, and then how to get the equations, and then what is the algorithm to solve those equations, because it was not directly, because we needed to do all this assumption stuff, right? Now we're gonna go a step further, and what happens if the problem that I'm trying to solve is not a steady state problem but a transient. It varies with time. As I said yesterday, everything is transient and everything is 3D. If you work with storage, if you work with, especially with storage technologies, you will always have to deal with transient problems, because you will always be involved in charging, discharging. You want to take what happens during the storage period, because I don't know, if I charge, let's say, a concrete block, then if it passes through 2 hours, because of heat losses, the amount of energy stored will be dissipated outdoors. So if you can go to steady state problems, okay, but usually the physics that will be related to your work will be transient. So then we need to move back. First thing you have to do is the same. I mean, there are 4 steps. First, which assumptions can you do? Second, discretize the domain. Third, get the equations. 4, algorithm of resolution. That's the path we have used for the steady state problem, right? Now it's the same. Assumptions, then the same assumptions. You have a domain, do the same. Like if you can apply symmetry, if you can apply constant physical properties, if you can apply whatever, but now it's a steady state, there is a transient, okay. Second step, discretization, that's the same. We divide the geometry, whatever it is, in the same way. Doesn't matter if it's transient or not. We have a solid, a liquid, whatever, we discretize, we divide the domain in different nodes in an ordered manner, so we will be able to put it in the computer, and the computer knows by the position of, in the case of 1D, the position of one index where you are in the solid. If there are 2D, then there's 2 index, one for this direction, one for the other direction, right? It's like where is the position? That's the same. Now, the third part, which is obtention of the algebraic equations, that's different. Now, for each node that we have, we will apply this equation. We don't have work. Let's assume we don't have mass exchange through the surfaces. So that's 0. So that's 0. That is 0. But now this is not 0. We have something varying with time, right? Usually in the heat transfer problems that we are working, there is no change in the kinetic energy, and there is no change in potential energy. But there is change of internal energy of the nodes, because they can change enthalpy in terms of changing the phase, or in terms of being heated or cooled down, varying the temperature. Okay? So we have this equation. Okay. That means that for each node, whatever shape you have in the node, I will have to compute whatever Q1, Q2, Q3. In principle, like the meaning of this equation is that the amount of energy, the powers that I have for a given delta time will vary my internal energy. That means if I'm adding 10 watts, if I'm removing 5 watts, I am removing 4 watts here, that means that the solid will be heated with a rate of 1 watt. If the delta time is 1 hour, that means that the amount of energy that will be stored in your domain during 1 hour with these conditions, under those conditions, it's 1 watt hour, right? That's the amount of energy. Under the boundaries of these powers, these heat transfer rates, because of this time step, because this pass of time, this volume with this density has the variation of temperature, and this temperature will be, this watt hour of energy, this unit of energy that I am storing in my domain will change the internal energy of my node. Usually, it increases temperature. Okay? That's the principle. Now, we have two options. Or we go directly to the equation, or I go step by step while we reach the equation. What do you prefer? It's up to you. It's not a lot of time, but maybe because of the hour, I don't want to lose your attention because I am now tricking with integrals and so on. So I will skip that. In case you want it, I can show you. But basically, what will happen is this stands for the boundaries that the node is facing, and that stands for the amount of energy that will be stored inside. If there is no phase change, that will convert into that. This term is the internal energy. Okay, actually it's enthalpy, but internal energy because there is no pressure change in this domain, it's the same. This term, this delta T, goes inside, and we have the same. Okay? So you can check units. This is watts. This is joules per kilo per Kelvin. Those are Kelvin divided by time. Those are kilos divided by cubic meter, and this is cubic meter. Cubic meter, kilos, Kelvin, joule divided by time, power. Okay? Good. So, yeah. Now, so for each node, we will do that. If I have whatever solid from remember that now the solution is the evolution of something. That means that I know where am I. For example, in the case of a fin, I will use that because you have the equations of the geometry and everything. That means that everything was at a known temperature. I know the initial conditions of the system. I know the temperature profile of the system. And then, suddenly, here was at 70, right? Yesterday, here we have a T wall at 70. Suddenly, something happens and this goes up to 150. Okay, how the system reacts to this change? The temperature of each position in the fin will be varying until it gets steady state conditions. Right? I want to see this evolution. Or imagine that air temperature is not constant. It's not 25. It has a sinusoidal profile, or any profile you want. So that means that the fin, I cannot do a picture of the fin and say, this is the temperature of the fin. No, no, no. Every time step, you will have a different picture. So, from something that you know, from some conditions that you know, let's say initial conditions, now, then something happens, something varies in time, and I want to check how this evolves. Okay? This is the concept of the transient. Imagine, you have, your storage unit is fully empty. You have a concrete block, everything is at 25 degrees. And you have a solar collector, there is sun, and from the solar field, you pump energy in the concrete block. Water at 80 degrees. Everything was at 20, all the nodes were at 20, and then start being charged. So how they are heated up? If there is a tube, for example, nodes nearby the tube will start being heated, and at the end, the corners will be heated. But I want to check the evolution, to know how much energy I'm able to charge in the concrete. Okay? This is the kind of problem we are facing now. Now, that means that, and I cannot solve, let's say, okay, I want to solve 1 day of the fin. Imagine this is still at 70, but the temperature of the air outside moves. I want to see the evolution of 1 day because of that. I cannot do it directly. I have to split the time into different time steps. I have to say, okay, what is the granularity, the resolution of your problem? How often do I want to check what is the temperature evolution? Every hour, every minute, every second, every 0.1 second, every when? I mean, I know where I'm starting, let's say 12 midnight, and I know I want to check all the day. But how long will be my steps? How big? I will say, okay, during 1 hour, those are the conditions. Then at 1 a.m., how my film will be? Or every half an hour, or every 15 minutes. This is important to select. What is your resolution in time that you will analyze that? If you say, okay, I want to have a root idea, so every hour it's okay. It goes faster. In case you go every second, it will take longer. Also, it's more accurate if you go down. Okay? I will tell you why. Imagine we do that for 1 hour. Every hour, I analyze. I do this equation. Okay, I analyze the conditions that passes from 0 to 1 hour. I have this picture. I want to have this picture now. Once I have this picture, I will go to the second picture. But I will move it sequentially. I cannot go from 0 to 24. I need to go step by step. First thing we will do, from 0 to 1. Okay? Now, if this is 1 hour, the algorithm says, okay, because of the boundaries in which you are staying, whatever, what is the temperature at 0? Let's say, imagine we have TR. This is a good example. Now, we start from at night, so it will be something like that. This is 0, and this is, I don't know, 0 degrees, for example. At 1, you have this, at 2, you have this, at 3, you have this, whatever. Here it's at 4 p.m., and so on, right? You have different evolution because of temperature. And this is 1, huh? Okay. Because of this temperature, I will have different convection here, right? I will have less or more convection in each node because the convection directly depends on the gradient of temperature. So the higher is the temperature outside, the more energy we get from convection, the lower, the more I dissipate, right? That means that these Q's depend on time. This is not a constant value. In the case, in the case of the film, if I am analyzing this node, for example, this convection depends on time. It's not constant always. We have conduction from the west and conduction going to the east. Those two also depend on time. Why? Because the temperature of these nodes changes. So they are not fixed. You are not having always the same conduction coming or going. So they depend on time. So that's why I cannot say, okay, this is your picture and that's it. No, everything evolves. So this depends on time, and this depends on time. Now, what it's saying is that the conditions that I have from 0 hour to 1 hour, I'm subjected to conduction, convection, and so on. The balance of heat going to the node will change the temperature from instant T to instant T plus 1. Will change this temperature of the node, and the node has this heat storage capacity, has this density, and has this volume. The more volume it has, the more energy can be stored. The more density it has, the more energy can be stored. The more gradient that is subjected, the more energy is stored. And the more Cp, the more energy. Right? During this period of time. Okay? Agree with that? Now, what is tricky here? The tricky part is where do we compute these balances? At 0 or at 1? So I have here a nice picture at 0. I know the picture. I know the boundaries, I know the temperature of the neighbors, I know the convection of each node, I know everything. And I want to know what will be the state after 1 hour. If I assume that from 0 hours to 1 hour, all the boundaries are the same as at 0, which is not true, right? Temperature outside, at 0, it's 0 degrees. And at 1 hour, it's -4, for example. If I am considering that for this jump, for the calculation of this jump, everything is at 0, then it's explicit method. Okay? If I am considering that the temperatures or all the conditions are as in the future step, as at 1, then it's implicit. That's the principle. Now we will go on the questions that you will understand, but that's the principle. The principle and the difference between implicit and explicit is that you want to figure out, to calculate what's the evolution from one place in which you know everything, okay, and how the boundaries in which it is subjected, your domain, changes. Okay, it changes, but under which boundaries? These ones or these ones? Because these ones are known, then explicit. And that, we can note it. If here I add T plus 1, it's implicit. If here I say T at instant T, then it's explicit. Okay? Let's do, as an example, one node. Okay? Questions? No? Now it's important you understand the concept. Now I will try to get the equations. Imagine we are doing this one. Okay. What we have here, before we were doing this, because it was a steady state. Now, it's not a steady state. That reports into a variation of the temperature. Then we are not in a steady state. Temperature is varying over time. Okay, temperature varies over time. Now, let's compute what is the summary of Q. We have, like, if this node, that is conduction, conduction, and convection. It's the same as before. So, QV minus QE minus Q convection equal to rho Cp Tp T plus 1 minus Tp T. Right? But this computed at, let's start with explicit, at the instant equal to T. That means, how is QW? Minus K, the same. R. Okay, nothing new. I'm saying, because of this, now this conduction and this convection doesn't have to be balanced. Before, yes. Before, everything in was everything out, because we are not storing anything. We are not changing the internal energy of the node. But now, yes. Now we have a modification. How it modifies? It changes temperature. It creates a gradient between one time step and another time step. Easy. And everything is computed at the time step from the past, in the known, in the comfortable area. You know everything, you know all the profile. Now you want to go further. But to go further, to analyze every node, you are assuming that all the neighbors and all the conditions are the same as in the past. So during this hour, everything was similar than in the past. That's explicit. Okay? So TP is computed in past, the neighbors are computed in past. So here, I have one equation, one unknown. Simple. This is your unknown. All the other, you know that. You don't have to assume anything. That's why explicit is not an iterative method. It's direct. But it has some disadvantages. Keep in mind that sometimes we say, okay, or you can ask me, how do you know the initial state? Sometimes you know, sometimes you don't. If you don't know the initial state, you have to create one code, one steady state problem, and the solution of the steady state problem will be the initial conditions for your transient problem. Got it? Or too much for after lunch class? No, you got it, right? Sometimes you run because you don't know okay, I want to check this, But I don't know what is the state of my fin here at the very beginning. So imagine everything here was at constant temperature. Okay, I ran the code that we used in the morning, and the output of that code was a map. That map I charge as initial condition. Now I start. I know the initial conditions, I know. It comes from another code. At time zero, I know. Where am I? I know all the temperature of the nodes, all the nodes. Now, after 1 hour, what happens? I know everything before. So, for each node, I have to compute the new temperature. But, luckily, the set of equations that I will have for each node will be one equation, one unknown. Directly solved. Actually, you know temperature at instant t, 0. You know the neighbors. You know those are constants. You know that the air temperature at the previous. You know the temperature of the node before. So this is just the only unknown. You can compute it directly. You pass through all the nodes, having these equations or whatever equation it gets. These and these, remember, they will have different equations. All the others is the same. Now, you finish. You're here now. You were at 1, at 0. Now you're at 1. Okay. Do you want more time steps? Or have you finished? No, I want more steps. I want to finish until 24 hours. I don't want to just know the evolution from 0 to 1. Okay, now your t is 1. And your t plus 1 is 2 a.m. So now I want to pass from here to there. But because I know all the map, at 1, it's direct. Okay? Any question? Okay, I don't recommend you to use explicit. Never. Because it can go crazy. It has limitations in terms of you cannot play with the grid as much as you want, and you cannot play with the time step as much as you want. There is a limitation. If I can show you. It will take me time to do. I don't want to. If you check it online, or if we have time to tomorrow or on Thursday, I will demonstrate what is the limitation. But there is a relation between the grid size and the time step size that you cannot overpass. If you overpass that, it didn't converge. Okay? And the limitation is like for 2D problems, M, which is defined as like this, where alpha was alpha was k divided by diffusivity. Okay, this is alpha. So this is the grid size. Imagine we have a square, and we have same grid like this, and we have the same size in this way and this way. Delta x and delta x, for example. So, if this value, this is the jump in seconds in the time, delta t. Here now we are doing 1 hour, whatever. If m this has to be always higher than 4, and if it's 1D problem, it has to go higher than 2. If not, it doesn't converge. So you cannot go as thin as you want unless you reduce a lot the time step. Okay? Maybe tomorrow or Thursday, if you're interested, I can show you why, or you can find it on internet why explicit has limitation. But I don't recommend you to go explicit because it's not iterative. Iterations ensures you convergence. Okay? Good. So I will look for the algorithm of resolution. Yeah. Now, if you are using explicit, what will be the algorithm? Input variables, the same. Calculation of coefficient, the same. If you need it, those are geometrical, right? So we know how to do it. Now, we need to charge the initial map of temperature. T 0 for each node. I need to charge to whatever map that I know. So the transience comes from somewhere you know everything and you know the evolution. You are going to calculate the evolution of that. But you have to start with something which is known. Some initial conditions, whatever it is. That's why Energy Plus has warm-up days. Because it starts and the whole building is at 25. Never the whole building is at 25. They always, the different layers, and the different nodes that you can imagine in a roof or in an envelope or a wall of a building, they will have different temperatures. So they start at 25, they run 14 days, and after 14 days, they start the simulation. That's why sometimes to create the initial conditions of your study, you need to run calculations before. Okay? But, in any case, you know the temperature profile at the beginning of your problem. Now, we define the time t plus 1 is the time at t plus the gradient in time that we're going to use, by definition. If I'm using a delta t of 1 hour, I might start at 0 hours, at midnight, then the t plus 1 time step is 0 plus 1, 1. Right? Easy. Now, we go to the Gaussian equations. So all these equations. I isolate this variable, I do that for each node, I compute it. Directly, I can do it. Directly because why? Because everything is known. I know all the temperatures, I know all the boundaries, I know everything. Because I am considering that from 0 to 1 hour, everything, all the surroundings of the node, all the conditions were the same as time equal to 0. After 15 minutes, it was the same as 0 minutes. After 30 minutes, it was the same as 0 minutes. Okay? Now, with this, I will get a solution directly. Don't need iterations. The only thing I have to ask is, do you need a new delta t? Do you want to explore more? Yes. Then, now, the temperature at time equal to t Now, my previous future, it's my new past. Again. Right? Now, I'm 0 to 1. Okay, now I'm 1. That was my previous future, 1. But now, 1 is past. I know 1. Now I want to go to 2. So to update that, I need to update temperatures. Now, at instant 1, I know instant 1. Now, t plus 1 means 2, the second hour. The same with time. The time 1 before was where I wanted to go. Now is where am I? I want to go to 2 now. I do that, and new timestamp. In this way I'm saying tt is 1. Now, t plus 1 is 2. 1 plus 1. Now do Garcia from 1 to 2. Okay. Anything else? Do you want more? Yes, I want more. Now, 2 is past. 2 is past. We go here. 3. And in this way, we advance until 24. Okay? If no, end. Finito. Okay? Any question? That's the easy part of the afternoon. Sorry about that. That's simple. There is no iteration here. But really, I will teach you what happens if we use implicit. If we use it. Now, is there any question here? No. Okay. Now, what happens if well, first thing is, as you can imagine, if we are considering that from 0 to 1, all the boundaries during all this period are the same as 0, we are going to generate a lot of error, a lot of deviation. So, imagine that I'm using a building. Is the building, the time stop of 1 hour reasonable? Maybe yes. But in the case of Finn, is the time reasonable 1 hour? It is not reasonable. Because it happens a lot of things during 1 hour. And during this hour, all the boundaries were the same as at hour equal to 0? No, they have varied a lot. You see it in the graph. But what happens if with the Finn, I say, okay, my gradient now is 1 second. Then, okay, I come 0 seconds, 1 second. Okay, doesn't change a lot, the boundaries. I can assume they are at the very beginning. As the only thing is that I will take 60 more time steps than in case 1 hour, 1 hour. Okay? So you have to be reasonable again. You cannot, people doing CFD, they are saying time steps of more than 0.1 second is nightmare, okay? But if you want to compute something realistic, like the performance of a storage unit after a full day charging, how do you compute every 0.1 second? Or every even 1 second? It takes a lot. So you have to be balanced between computational cost that it will take to you and accuracy. So each 1 hour, I mean, Energy Plus usually use 1 hour. And I think the thinner you can go in Energy Plus is 10 minutes. I think you cannot go less than 10 minutes. So you cannot even simulate with a resolution of less than 10 minutes for a building. But for a building, it does make sense. Because the boundaries that they are subjected doesn't change a lot every 10 minutes. Okay? Now, interesting part. What happens if now I don't want to compute, I want to see the evolution of temperature from an instant and the past and future, but I will assume that the boundaries surround me are not the ones from the past, but the ones from the future. Then I have here t plus 1. all the convection at t plus 1, all the conduction coming from the west at t plus 1, and the conduction going to the east at t plus 1. That's coming interesting. Plus 1, everything is plus 1. So conduction and convection is computed at the future, in which I don't know anything. Okay? That's implicit. But now I have a problem. Because my unknown is the same. Is this one, is this one, and is this one. But I don't know the temperature of the west node in the future, and I don't know the temperature of the east node in the future. But I can do the same trick as I did yesterday. We can assume values. Okay? So I will have. Do you want it? Well, I can do it. Tp t plus 1. It's equal to. You will have this. For each node, you will have this equation. Note that I'm going to name this B, I'm going to name this C, I'm going to name this F, I'm going to name this D, and this is A. Sorry, I'm missing. But this is, now I will have the same problem as I had yesterday. I don't know this value, I don't know this value. So I have to assume. The principle is the same. What I'm going to do, as a concept, I want to calculate the temperature of my node with the conditions here in the future. From 0 to 1. Okay. But I don't know the neighbors. I assume the neighbors. I assume all the map. And I say, okay, imagine, just as a start, that the map is in the future with the same temperatures as in the past. We start here. Okay? Then if we assume this, and we assume this, I can calculate. Right? I compute that. So I compute all the nodes. And again, I will have a map of solution and a map of assumption. Was it correct? No. First, you saw it in the morning. We needed 25,000 iterations to get. So here, almost the same. Now, assume that the conditions in the future are the solutions and pass again through the equations. New set of assumptions, new set of solutions. Are they the same? No. Charge it again until it converge. And you have assumed one thermal map of the film, and it was correct. So everything was coincident. I mean, everything was converged. Everything is okay. So now you say, okay, now I'm on one. More time steps? Yes. Okay. Restart iterations. Now I don't know the conditions at 2. I know at 1. I assume the ones from the solution. Pass through the equations. Is it the same? No. Try this. Is it the same? No. Try the solution. Try solution. Try solution. And it is like, yes. Okay, now I'm at 2. So imagine, I have to do it until 24 hours, for example. Every second. Or every whatever. So now it takes more time to come. Not the click and run is not that easy. It takes a little while. And this is for 1D problem. So you have, I don't know, 100 of nodes. 100 of equations every iteration of every time step. Imagine 2D, 3D. That's where you start to have computational problems. Okay? So, I will try to write the algorithm here. Input, coefficients. Now start initial map, like T. New time step. Now, before we go to the equations, before we go to the Gauss-Seidel, the equations that we have defined for each kind of node, I need to create a map of assumption, right? Something where I start. So now, my map of assumption I can say, okay, I will start assuming that all the nodes in the future are the same temperature as the nodes in the past. Okay? Now, it can happen if your heat transfer coefficient, if your density, if your viscosity, if something is not constant, and you are not using constant physical properties, then with this assumption you need to compute them. You need to compute density, you need to compute conductivity, heat transfer coefficient, density, whatever, and then go to the equations. But because maybe this value depends on the temperature that you have assumed. Do you follow me? That's where it gets interested also. It becomes interesting. So there, okay, I want to have perfectly the model with all the physics, all the complexity. Okay, good luck. If you can, yesterday, what I said, if you can simplify, do it. If the variation of a thermophysical property is very important, then you have to add 100%. If it's not critical, to do it. Because now, before you go to the equations, you have to compute more things. The equations will depend on this. Imagine we have used constant. Then, Gauss-Seidel. All the set of these equations. For I equal to 0, one equation. I equal to 1, one equation. I equal to whatever, one equation. But from this assumed map of temperature and these equations, I can create a map of solutions. Correct? Is this map of solutions the same as yesterday? The deviation between the map that I assume for the future and the map I got in the solution in the future, it's below the error I want to accept or not. Now I have to do a... Okay. That's why I have colors. That's a question. No, it's not the same. We are not going to reach the convergence at the very start. So my new assumption will be again the combination between solution and old assumption, and the relaxing factor will be the variable that will mix the two, right? That's the old assumption plus R multiplied by solution minus old assumption. This is the same as yesterday. I have tried one map of assumption. I run the equations. I got a map of solutions. Is it the same? Usually no. It's not the same. So you have to retry again. What is the new assumption? Okay, the new assumption is a mixture between what you have assumed in the past and your solution. You have a new set of assumptions. Now, where do you get now? Pass again through the equations. Now I will have another set of solutions. The solutions and the new assumptions are the same? No. Create a new assumption. Do this until it's the same. When it's the same, good, you have been from times the 0 to times the 1. Now you know 1. Now following question is, do you want a new delta t? If no, dinner. End. That's it. But usually you are not going to create all this for just one times time. You want to have more. Usually it's for a long period. So usually you need yes. And if this is the case, again the old future is the new past. Right? I was going from 0 to 1, but now I want to go from 1 to 0. From 1 to 2. So 1 now is past. I know 1. I want to go to 2 now. So I have to update temperature and time value. And then, okay, now I want to move from 1 to 2. That means t plus 1 now is 2. Because it's 1 and 1. The assumption of the map of temperature at time 2 is the solution I got. The first assumption is the solution I got at time equal to 1, because I have to start from somewhere. Go and do the equations, the same equations, but now they are going to be used not from 0 to 1, but from 1 to 2. Now I got the solution. Is the solution the same as assumption? No. Go back, refresh, refresh, refresh. It got, yes. Do you have a new time? Yes. So now from 2 to 3, and do like this. Okay? Do you understand the concept? Yes, right? Any question? No? Okay. Then I can show you this into the computer. Okay? Same case as we did in the morning. But now the heat generation is switched on. So everything was at a given temperature, and suddenly something switches on the QV. And I want to know how the solid evolves from a steady state until it gets another steady state. Okay, let's see. Do you want to do a short break? Yeah. 10 minutes? Okay, let's do 10 minutes. So we see you in 20 past 4, okay? Yeah, I had two coffees at lunch. Yeah.
I suppose from this.
No.
Just
Oh, yeah. Every time, I mean, now we are at 0, we know 0. Time step 0, we know. Now we want to know 2, 1. But we don't know all the temperatures at time step 1. So in the equations, no, in implicit. So the difference is that if I am using explicit, it means that from coming from 0 to 1, I assume that everything is like at 0. If it's implicit, everything is at 1. So that means that this is at time t plus 1. That means that this is at t plus 1, this at t plus 1, this at t plus 1. Which means that the temperature at t plus 1.
Yes.
And you don't know.
Yeah. Okay.
You don't know what is the west temperature or the east temperature of the neighbor in the future. You don't know. That's what you need to assume.
Okay. So you have like.
You have all the nodes
Yeah.
at 0. You know what they are. Now something happens.
So you assume like a profile for the.
At 1, you assume one profile. Then you pass through the equations. Like here. So you assume whatever profile you have. You have the initial. Now, asterisk means assumption. The future, you assume whatever. Now, go to the equations. Because you have assumed, you can close the equation. You can have a solution. Now, the solution you took and the assumption, so the solution in the future and the assumption of the teacher, is it the same? No, it's not the same. So refresh the assumption.
And so, yeah, so this
TR, that means that this is a vector of all the nodes.
Oh, okay. Ah, okay. So this one means,
This is the past?
and because it's the sum I gave you.
Yes. Yeah.
Okay.
So no, I mean, this is known. This is known.
Okay. Yeah.
So this is temperature at time equal to V.
Ah, okay.
This is the past. Now I want to be from T to T plus 1. I will move this direction. I know this. And I want to move to here. Okay. Then, because I don't know anything about here, I have to assume that all the map is like in the past, as a first shot, first assumption. Right? Now, I will go through all the equations. Then I get,
The new one.
I have a solution. Is the solution the same I have assumed? No. Okay, I need another assumption.
Okay.
And the new assumption depends on the old assumption and the solution. Now, with the new assumption, go again to the equations until it converges. Now we have this. The temperature here, it's known. It has converged. The assumption and the solution was the same. That means that the solution is correct. Now, do you know another time step? Yes.
Yeah.
Now, T plus 1 is T, and I want to go here.
Yeah.
That is why. And you start here. Now I want, before I was going from 1 to 0 to 1. Yeah.
Okay, so my new step here is this one.
Yes.
Okay.
And as a first shot again, I will assume that everything in the future is the same as in the past. It is not, but it is as a first shot. Okay.
Nina, tu perché hai messo a cartellare a Jessica Spinetta? Sai dov'è?
L'ultima cosa che mi hai detto.
Yes. I mean, this is why the case in Greece.
Let's see what it is.
Thursday. Okay. You have some very nice tradition.
No, actually, if you're working here, if you want to start second.
It's more suitable for
Perfect.
segregation. Yeah, but there's a bus. And the brains and the tickets are big one routes. I will check it. It's pity that from Rome there's no direct train. Right. Yeah, but they're not job. Late. You meant the lake that is nearby? Yeah, on the I go like this and then turn right Perugia.
Because you change the train, not the back. They will change. That's what you go around.
Yeah, when I came when I first came here, I came with a train from Rome. And I had changed 3 trains.
Can you see it more or less?
Well, drinks or change 2 times?
One from airport to Rome, and then there's one direct. And then one that stops.
Yeah, that's possible to. I check from there to Timbustina and then from Timbustina to here and have to take 2 trains.
But there's
That
a
change
there's
to-
a and there's also a bus that goes from Chino to here there.
Yes, been talking about
Usually if you say distance, 25%. So then
If you have a student's card.
yeah, but you can download the card. I actually I wanted to show the card.
You have a card, maybe it's here.
It's like online.
Okay, so here you also have in the email this file. So it's the problem that we solved this morning of 2 layers. Now everything at the beginning is at 25, and then generation of heat started in the part of the solid A. Okay? And I want to see how the temperature of the whole solid evolves because of that, which goes up. Now the definition, it's very similar to the one I have used this morning. So we will include all the libraries, the main. Now, in the definition of the temperatures, you use double for temperatures for sure. You use a static in case you think that the memory required to move this matrix are higher than your RAM memory, your PC, your computer, or your whatever. If not, you can delete static. But now, matrices has 2 dimensions. Temperature will depend on position, but also will depend on time. And for example, I want to compute the evolution in 24,000 time steps. Okay? For example, every second. Imagine time step is 1 second, then 24,000 seconds. If time step is 1 minute, 24,000 minutes, whatever you like. So I need this dimension of a matrix for the temperature, for the assumed temperature. Also I have another one. So you can think that this dimension is actually 4.8 million of values, right? This also 4.8 million of values. That's with 1D. If it's 2D, you have to multiply. That's why you need to keep things as simple as possible. Now we don't need 200 nodes to determine that. Probably we don't need 24,000 time steps, but that's just an example. Number of iterations. Before, it was a value, j, and that's it. Now, we will have different iterations per time step, meaning that from passing from 0 to 1, maybe I need 25,000 of iterations. From 1 to 2, I need 15,000. So every time step requires a number of iterations, right? So I will store this number of iterations because it's for teaching. Maybe you're gonna use it, but I recommend you to do it because if your model is being slow, or you think this is slower as I expected, run this and you can check what is happening when you're having a higher number of iterations. If the model requires big number of iterations, that means there is something happening there. Maybe it's because you are modeling a PCM system and the phase change starts. Okay. Maybe it's because you're in a transient process and then sun appears. And you need more iterations to converge. Okay. But make sure that it's because something happens physically in your problem, not because some numerical issue. Yeah? Then we have conductivity, we have density, we have CP, we have generation of heat, we have heat transfer coefficient, we have the maximum error allowed, we have delta H1, delta H2, that's the same as in the morning, TR, relaxing factor, initial value, Y, the index that will count in the geometry, I equal to 0 means at the beginning of the wall, I equal to n plus m means at the outer environment, T, that will be the index that will give me in which time step I am. In 0 time step, in 1 time step, in 2, in 3, no matter if the time step if every 20 seconds. Time step 0 means 0 seconds. Okay. Time step 1 means 20 seconds. Okay. Time step 2 means 40 seconds in real simulation. Okay. But it's 0, 1, 2, 3, 4, and that's where here we are moving in this part of the matrix, in this dimension of the matrix. Okay? J is the index of the number of iterations. So for each time step, maximum number of iterations that I allow, 100,000 for each iteration. M, number of nodes in each part. Delta T, how big is my time step? I will jump from 0 to 1, but this step, how long is it? 1 hour? 2 minutes? 1 second? 0.1 second? Whatever. We define here. Then we have the error total, as in the morning, error, then some coefficients that I will use for simplified equations, A, B, C, D, E, right? Then time, which actually I do it for the print, you will see it. Number of iterations, the n, where is the n? It's the total number of time steps that I will run. If, imagine I'm jumping 1 hour from 0 to 1 hour, 2 hours, 3 hours, until 24 hours. So num_t is 24. It's the n, the last iteration I want to use. In this case, probably 24,000. Thickness 1, thickness 2. Clear? The real only change is that temperature now also depends on time. That's it. But it's transient, it depends on time. the map of assumption also depends on time. Okay? Now, first thing we do, input parameters. The air is 25. Initial temperatures, imagine everything is at 25. The wall, the air, everything was at 25, then I switch on the heat generation. But before, everything was a steady state. Everything was at 25. I know my first position, I know my first position. All the nodes in the wall are at 25. Now I switch on. Then after one time step, how is it? I don't know, I have to calculate. But I know this. Heat transfer coefficient constant, then thermal conductivity constant, density, Cp, and Qb. Now we need density, we need Cp, right? Because in some parts, in this part of the equation, I am accumulating heat. So I need to know the joules per kilokelvin that the solid can store. I need to know the density of the material. Because based on the volume of the node, I will take into account how much energy I can store there. Thickness 1, thickness 2, that's the same as in the morning. Definition of maximum error, definition of number of maximum iterations, Raxin factor 0.9, for example. Number of nodes, 10 and 10. Now, calculation of coefficients, that's the only calculations I need. Delta H1, delta H2 are by definitions theta 1 divided by n, theta 2 divided by n. True? Yes. Number of total iterations, 23,000. For example, whatever you like. I want to compute, and my delta t, the increment of time, is 20 seconds. So I will do 23,000 jumps if each jump is 20 seconds. Okay? Okay? Now I start. Start from t equal to 0, from the very beginning, and the node also from the very beginning. First thing I do, I do this. I charge initial conditions. I know everything is at 25, right? So I'm doing this. T initial, I set that a value 25. I charge the array of assume and the array of solutions as 25. Correct? I'm doing this, nothing else. Now, let's start with the Gaussian. Or we start with the set. This loop will be in a while. The command is while. And it will execute all these lines while t is below maximum number of iterations. So until this question is no, do you want to explore new delta t? Until this is no, it has to have this loop. This loop in the code is this one. So while t, the index of the jumps 0, 1, 2, 3, it's below 23,000, you have to run. Okay? Run. First thing we do, t is equal t plus 1. Now we are not at 0. We want to go to 1. Okay? First thing we do, we assume we need to have an assumption. And the map of temperature in the future, I assume it's the map of temperature I have in the past. I know in the past. That's what I do here. How? With a for. We cover all the geometry, as in the morning. For I equal to 0 to I equal to n plus m, I plus plus. So do this for all the nodes. For all the nodes, the assumption in the future is the solution in the past, t minus 1. Okay? There, here, sorry. Past is t, and future is t plus 1. Okay? Now here is future is t, and past is t minus 1. It's the same. Do you follow me? Okay. Let me drink. Now it will be the same as in the morning. Exactly. Now I have these assumptions. Now I can go and do the second loop, which is this one. It's the form of the iterations. The 4 in J. So I will start from 0. Now, error total is equal to 0. I need to reset this to 0 so I can compute the error at the end. Now, explore all the domain. From 0 to n plus m. Is it 0? Yes, we are in 0. Go to these equations. Now, B stands for what is coming from the west. C, what is going to the east. D, generation of heat. E, the inertia term. Density multiplied by Cp multiplied by the volume divided by delta T. This term. Right? Actually, how I get that? E. This is E. Right? And A, which is the denominator, is B plus C plus E. Yes? And in that case we have convection. It's the same. It's the same way we got these equations, you get any other. Okay, in this way, because we know the assumption temperature of I plus 1, it means the node in the east at the future, at time, I know the temperature of the node in my previous time step, Tp, I can calculate the temperature of the node, P, in the future, T, for I equal to 0. Then it's the same. I will go I equal to 0, I enter, I got a solution. If I is higher than 0 and below n, no. I is 0. Okay, I don't enter here. I don't enter until the end. Then goes back to the 4. This 4. Is I below n plus n? Yes, it's 0. And then plus m is 20. Then at one value, 1. Go here. If I is equal to 0, no, it's not equal to 0. It's 1. I don't enter here. I between 0 and n, yes. Go inside. Execute these lines. Now, it's the same. It's long, but it's very structured. So at the end, it's always a lot of copy pasting. Be careful because this is different as this. For example, this has no conduction, this has conduction. This has half of the thickness, this has full the thickness. Actually, here there is a mistake. No. This is half of the thickness, there is not half of the thickness. Imagine, here, if you forget about these two, it's wrong. So, I told you, there's a disadvantage. There's a lot of troubleshooting here. So try to be concentrated when you're doing that. Nodes inside the material A, node between material A and B, material B, edge. Okay, I calculate the errors the same way. But now my unknown is at time step T. Good? Assume map of temperature at time step T. Solution map of temperature at time step T. Is it the same? No. Calculate the error. Is the error higher than the maximum error allowed? Yes. I need to refresh my assumption. And go back. It cannot break because the error is higher, so this goes back to the J. Now J equal to 1. Go again. Refresh error. Go and explore all the geometry again. Go 0, from 0 to n, until the end. Is the solution equal to the solution? No. Go back. No, go back. No, go back. Yes. Okay. Yes, it's the same. Break. I break that for. Here, I save the iteration j, the index of the number of iterations, into that array, which is saving for me the amount of iterations at every time step. This is useful, I told you. Now, here we have the while. This is the break of the while. This is stands and goes up to here, and ask. T is below the maximum number of times I want to use. No, this is 23,000, and I am t equal to 1. Okay, t equal to 2. Repeat the process. Until it goes here and says t is not below number of t, the maximum. Then I can go and print results. Now, printing results, it is not easy as in the morning, because it's not just a picture, but it's a video, what I want to show. So it's, I will create one column, which will be time, then temperature at the beginning, temperature in the middle, temperature at the edge, and number of iterations. That's the table I want to create. Time, what is time? The index t, 0, 1, 2, 3, 4, multiplied by delta t, 20 seconds. So, in one column I will have 0, 20 seconds, 40 seconds, 60 seconds, and so on. Right? And in the other columns I will have temperature, depending on time. But I have to print for every time step. To do that, you can do a while also. It's a loop. It's a way to say, okay, print time, compute time, print the temperature, print all the temperature iterations, and do line. Now, t is equal to t plus 1. This goes with this. Again, while. Is t equal to 23,000? No. Do it again. Do it again. In this way, we print the results. Question? And we finish. Okay, let's execute it. Finish. Let's see. I will go for Excel. Data. You can do it with Python or whatever you use. This is basic course, transient. Okay, so we have this. We have this evolution. Remember those values? 28 point something, 28, and 27.5. They were the solution from the morning. Because everything was at 25, then I switch on, and after some seconds, I got a steady state. And the steady state was the solution not before, in the morning. It has to be this way. Okay, that's why sometimes you need to run before a steady state. Imagine now I switch off the QB. My initial is this one, and then I switch off. And I want to know not this run, but the run up to 25. Because at the end, everything will be set at 25. If air is at 25 and there is nothing else, everything is adiabatic, all the solid will remain at 25 at the end. Right? Number of iterations. we have 79 at the first, and then reduce until 0. Why we have more iterations at the beginning than at the end? Because there were more gradients at the beginning than at the end. From everything at 25, everything perfectly at 25. Now, some excitation. I'm having QB there. Something is moving. So from 0 to 1, it takes me a while, only 79 iterations, not much. It took me a while to get that. Now, everything is slightly moved. So from passing from 1 to 2, it would cost me less, 78. From 2 to 3, 78, then 77, because everything is more adapted. Everything is more, less repentino, I don't know how to say it. Yeah, okay, I know, I speak Italian. It is less suddenly happen. Okay? Any question? No? Okay. We still have 10 minutes. I think you have these files, you have it in the email. So now they work. I know you usually will not use 1D modeling, but now I would like to talk, because we have been doing with simple geometries, but let's see how we obtain the equations if there is a pipe, for example, or there is 2D, or there is any different kind of solid. Okay? It is important that you understand the principle, and I think it's simple. It's not rocket science. We are just trying error, and guiding the algorithm to get the solution. Because why? Because my new assumption relies on the physics, relies on the energy equation. I'm not just assuming by random. My new assumption is a solution of something. So it has to converge. There's no other chance. Okay? Okay. If it's 2D, you will have arrays like this in right? And the 4 that you will use will have to explore all the domain. How many different nodes do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. True? That's a 2D in Cartesian, for example. From 0, 0 to n0, 0m, nm. Right? This is 0, 0 node, this is n0, this is 0m, this is nm. In the computer, how do I explore all these? For I equal to 0, meanwhile I is below or equal to n I++. Now, if I am in 0, if I am here, Now I don't have only one node. I have all these nodes. Right? What should I do? Another 4. I have to run all these. Now inside the if, for j equals 0, meanwhile j is below m or equal to m, j plus plus. Now if j is equal to 0, whatever, equations, this node. If, one box, if j is higher than 1 and below m, another box. We are in all these nodes. But we are inside if equal to 0. Because we are in these nodes. If j is equal to m, another box. Remember, in C, this is for asking. And this is for assigning value. That's very important. If you put in one if this, bye-bye. Because it will impose this value to j. You are not assigning the value, you are asking, is m? Now, when we finish this for, and we finish the if. Now, if is not 0, and if I is higher than 0 and below n, do another for. And the same. If you are not at this edge, and you are in this area, then another 4. You follow me? So it's a 4 inside another 4. Because you are not exploring just in one direction. You need one loop to explore in the I direction, and you need to explore another one in the Y direction. Or in the J direction. Okay? This is how it goes with 2D. If you have a node in 2D, it's the same. Conduction coming from the west, conduction coming from the south, conduction going to the north, conduction going to the east, and accumulation. For example. Same equation. The only thing is that you have 2 more heat fluxes. So what? You are not going to do the operations. The computer will do it for you. You just have to write it down. Instead of having B, C, D, you will have more. Okay? So what? This will stand for B, C, D, E, F. Okay. You add it. That's it. But for each, you have different equations. Remember, you will have 9 different equations. 1, 2, 3, 4, 5, 6, 7, 8, 9 different types of nodes. Everybody follows? Good. Any question on that? No. Let's say some words. What's happening if... Are you very tired? No? Need a bit, right? 5 minutes. What happens if, or what I do when I am simulating a pipe with a fluid going inside? Were you? No. Yeah, this was copy, more or less. Typical problem, and you need numerical model to do it correctly. Is, imagine you have a pipe in the outside and you want to, you pump hot water, any district system, any anywhere. You need a centralized heating system, for example. And you want to know at what temperature the water arrives to your home. It's subjected to heat losses in the path to your home. How do you calculate the temperature? You know the temperature at the inlet, you know the mass flow rate, you know the pipe, you know the insulation, you know temperature outside. How do you calculate the temperature arriving to your home? There is no analytical solution for that. Analytical solutions remains for constant heat flux in the surface or constant temperature in the surface, which in reality is not the case. Okay? So, how do you compute that? You need modeling to do that. So, imagine we have a pipe, a steel, and insulation. This is a pipe. I assume it's axisymmetric. It means that the node touching the water is the same for all the surface. It's at the same temperature. It doesn't care if it's, if I watch in this way, my nodes will have this shape. This is water, and that will be my first node. That will be my second node. That will be my third node. And the last node, for example. But I assume that all these is at the same temperature. Is this correct? Yes, right? It's a 2D problem. We have variations of temperature in this direction and in this direction, but not in the radial direction. I don't have difference between here and here. How? They are subjected to the same. So, this is actually a typical problem of axisymmetry. Okay? Okay. So these are my nodes. I need to compute a surface here because I need convection. I need to compute surface between nodes in the same way I did it for the fin, because I need to compute conduction between this node and this node, right, inside the pipe. So here, what I do is I discretize the fluid only in the axis direction. Only. One node of water, second node of water, third, fourth, fifth, sixth, whatever. I know here there will be a boundary layer and there will be a temperature profile. But if you want to do this, you have to go to CFD. Because you will need momentum, you will need mass, conservation, and energy. Navier-Stokes equation you will need. And it's really difficult to program it in the way I teach to you. So I assume plug flow. Plug flow means that all this water is at an average temperature of whatever. And there are no gradients inside that affects the heat transfer. All the heat transfer coefficients, all the Nusselt correlations that are developed in the literature are for plug flow. Right? So you can estimate this heat transfer coefficient, right? For this, depending on the water temperature and surface temperature, you can go get air density, air viscosity, air conductivity, compute Reynolds, compute Nusselt. You have heat transfer coefficients. All the correlations in the literature are prepared for that. Okay? So I just divided the fluid in this way. Now, solid. One type, inside the metal, another type, another type, another type. And at the end the same. These are the different type of nodes that you will have. Everybody agrees? I will need to develop energy conservation equation for this kind of node, for this, for the ones touching the water, for the ones inside the metal, for the ones between the metal and insulation, for the ones inside the insulation, for the ones looking outside. And this is the only way to estimate, okay, I know temperature here, what is this constant heat flux? No. Imagine this is 80 degrees, and I don't know, this is going to be 72. This is not constant heat flux. It's not losing in a constant matter, in a constant profile, the heat. Because this is warmer than this one. So that will lose more energy than this one. Heat losses will be more intense here than here. But in the literature, there's an analytic solution for that, for constant heat flux or constant temperature. Is this constant temperature? No. Because the temperature of the surface will depend on the temperature of the fluid. And the fluid is not constant. Maybe this is not constant. Maybe this is not constant. Usually this is not constant, and also usually this is not constant. So usually you need numerical modeling to do this. Okay? Any question? Now, here, and we will do it first thing tomorrow. When I apply energy equation to here, remember the energy conservation equation that we have been using? We are always deleting the last term. Because I was saying there is no mass exchange. These, they have mass exchange. There is some mass moving from left to right. So then that term, we have to consider that term. Okay? But we will do it tomorrow. Thank you. Can you cross, please?